This is Colin Selleck of Binghamton University. This is a video tutorial on chapters 12.1 through 12.2 of Dynamics by R.C. Hibbler. Today I will introduce dynamics and speak about rectilinear kinematics, continuous motion. First, let's define mechanics. Mechanics is the study of how bodies react to forces acting on them. It is divided into two subjects. Statics, which you should have already taken, is a study of bodies in equilibrium. That means the body is at rest or traveling with constant velocity. The other subject is dynamics, which is the topic of this course. It is divided into two subjects: kinematics, which is concerned with the geometric aspects of motion, and kinetics, which is concerned with the forces causing the motion. Today's objectives: you will be able to find the kinematic quantities position r, displacement s, velocity v, and acceleration a of a particle traveling along a straight line. Activities include applications, the relationships between r, v, and a for general rectilinear motion, the relationships between r, v, and a when acceleration is constant, and some problem solving. Some applications. Why do we study dynamics? Well, the motion of large objects, ships, planes, automobiles, can often be analyzed as if they were particles. Now, a particle has mass, but negligible shape and size. We're also ignoring any rotation of the object. So one example is, if we measure the altitude of this rocket as a function of time, how can we determine its velocity and acceleration? Here's another example. We have a race car. What if we put an accelerometer in that race car, and we measure the acceleration as a function of time? How can we determine its position and velocity as a function of time? Here's a motor-driven pump system. We have a motor here driving a pump. Can we determine how much torque is required on this motor to drive the pump? Can we predict the system performance? And helicopters and airplanes vibrate a lot, and there's sensitive avionics on these aircraft. How do we characterize the vibrations? How do we test these systems? Here's the Bell rocket belt from the 1960s. Can we characterize the performance? Can we calculate how much thrust is required for liftoff? All of these problems can be solved by dynamics. So let's move into section 12.2, rectilinear kinematics, continuous motion. First, some definitions. A particle P travels along a straight line path defined by the coordinate axis S. Now, the position of the particle at any instance relative to the origin is defined by the vector r, or the scalar s. Typical units are feet and meters. Now, the displacement of the particle is defined as its change in position. So delta r is the change in position, and it's equal to the new position r prime here, minus r. We can also define the total distance traveled by the particle, s sub t, which represents the total length of the path over which the particle travels. Now let's define velocity. It is a measure of the rate of change in the position of a particle. It's a vector quantity, so it has both magnitude and direction. The magnitude of the velocity is called speed, with units meters per second or feet per second. So the average velocity of a particle during a time interval delta t is just its change in position over change in time. However, the instantaneous velocity is the time derivative of position. So velocity is dr dt. Now speed is just the magnitude of the velocity, and the average speed we can define as the total distance traveled divided by the change in time. Next, we have acceleration. That is the rate of change of the velocity of a particle. It is also a vector quantity with units of meters per second squared or feet per second squared. Now, the instantaneous acceleration is the time derivative of the velocity, so it's the time rate of change of the velocity, dv dt. Acceleration can be positive or negative, and we can manipulate these last two equations. A equals this one right here, a equals dv dt, and v equals dr dt. We can eliminate time and come up with this equation here, AdS equal vdv. So here's a summary. We can differentiate position, ds dt, to get velocity and acceleration. We can integrate acceleration to get velocity and position. Note that s naught and v naught represent the initial position and velocity of the particle at t equals 0. Those are the initial conditions. Here's a special case. This is only true when the acceleration is constant. So we can integrate those equations to obtain some very useful equations A common example of constant acceleration is gravity. For instance, a body in free fall towards the Earth. In that case, the acceleration is g, or 9.81 meters per second squared, or 32.2 feet per second squared. So let's look at these equations. So we can integrate the acceleration over time to get velocity. Since the acceleration is constant, it results in this equation here. Velocity is the initial velocity plus acceleration times time. We can integrate the velocity over time to get position, and we come up with this equation right here. S is equal to the initial position plus the initial velocity times time plus 1/2 at squared. Now, if we know the acceleration is a function of distance, we can integrate this equation, and this yields a change in velocity. So we can get v squared is equal to the initial velocity squared plus 2 times the acceleration times delta s. Let's look at an example. So a particle travels along a straight line with velocity defined by 4t minus 3t squared. Find the acceleration and position of the particle when time equals 4 seconds. So what's our plan? Well, we have v as a function of time. We know that acceleration is dv dt. So it seems that we can differentiate the velocity to get the acceleration. And to get the position, we know that velocity is ds dt. So v dt equals ds. So it seems that we can integrate this to get the position. So in this case, we're going to differentiate, and here we're going to integrate. So let's do that. So let's take the derivative of the velocity to determine the acceleration. A is equal to dv dt. So we want the derivative of the velocity, which is 4 minus 6t. So when t is 4 seconds, we plug 4 into this equation. We get 4 minus 24, or minus 20 meters per second squared. The negative sign indicates it's in the negative direction, or towards the left. We can calculate the distance traveled in 4 seconds by integrating the velocity. So here we have the integral of the velocity as a function of time, and that comes out to be 2t squared minus t cubed, and we substitute 4 seconds in, and we get the distance is minus 32 meters, or it means 32 meters to the left. Here's another problem. This time we have velocity as a function of distance. We want to find the velocity and acceleration as functions of time, if that's equal to 2 meters when t is equal to 0. So what's our plan? Well, we want to find the velocity, and we know that is ds dt, and we have velocity as a function of distance. So we should be able to use this equation to get the velocity. And once we get the velocity, we know the acceleration is dv dt, so we can use this equation to get the acceleration. So velocity is ds dt is equal to minus 4s squared. Collecting terms, we get this equation here. Now we can integrate that equation to get the distance. So we integrate from 0 to t. At time t equals 0, s is 2. So this integral comes out to be this right here, which simplifies to this. So now we have an equation of distance as a function of time. Now that we have this s as a function of time, we can take the derivative of that to find the velocity. So we do that here, and the derivative of this equation s with respect to time is this right here. Now we know that acceleration is dv dt. Now we have an equation for velocity, so we can integrate that to come up with an equation for the acceleration. Some important points. Dynamics is concerned with bodies that have accelerated motion. Kinematics is the study of the geometry of the situation. Kinetics is the study of the forces that cause the motion. Rectilinear kinematics refers to straight line motion. The speed refers to the magnitude of the velocity. The average speed is the total distance traveled divided by the total time. This is different from the average velocity, which is displacement divided by time. A particle that is slowing down is decelerating. Note that a particle can have an acceleration and yet have zero velocity. And finally, the relationship AdS equal VdV can be derived from these two equations by eliminating time. So here's a summary of the equations you should take away from this lecture. Velocity is ds dt, acceleration is dv dt. You can combine those two, eliminate time, and come up with a equal v dv ds. If the acceleration is constant, these equations reduce to these three equations right here. Some problem-solving techniques. Dynamics is very involved because we take into account the forces applied to the body and the motion. We also use calculus a lot rather than just algebra and trigonometry. The most effective way of learning dynamics is to solve problems. This is very, very important. Homework problems, example problems. To be successful, we should present the work in a logical fashion. So follow these 6 steps. Read the problem carefully. Try to figure out which theory am I going to use. Draw any necessary diagrams, so free body diagram perhaps, and then tabulate the problem data besides that diagram. Establish a coordinate system, and then apply the relevant principles. Solve the necessary equations. When you get your answer, this is the gut check. Study the answer and say, does it make any sense? Did I get an acceleration that is orders of magnitude greater than anything else? And once a solution has been achieved, determine if you can solve the problem in perhaps a different way. And if so, solve it in a different way and compare your answers. When you solve problems, please do your work as neatly as possible. This stimulates clear and orderly thinking. This concludes this lecture. The next lecture is 12.3, Rectilinear Kinematics, Erratic Motion.